This is the first video in a module on mechanics in non-inertial reference frames. Until now, we have tried our best to avoid working in non-inertial frames, primarily because Newton's second law and the first one are not valid in non-inertial frames, which can lead to problems. Particularly when we're working with Lagrangians, it's very difficult to know how to write down the kinetic and potential energy properly in a non-inertial frame. So for that reason, we restrict ourselves to inertial frames only, but that will change now. It turns out that in many cases, it's very convenient to work in non-inertial frames. For instance, the surface of the Earth is not an inertial frame, because the Earth is rotating and it's orbiting around the Sun, and all those things add net accelerations. So only in certain circumstances can we neglect those and say that and treat the lab environment where we live our lives to be inertial. So for that reason, it will turn out to be very convenient to develop a framework in which we can actually do mechanics in a non-inertial frame. And that's what we're going to do now. First with frames that have linear acceleration, and later with frames that rotate. But we'll start with the linear case here. So let's say here we have a frame, and we're going to call this frame S0. The coordinates are given by X0 and Y0. And then we'll have, and this is an inertial frame, and we will add to it another non-inertial reference frame, like this. Let's make it red just to make it clear. We're going to call that frame S. Okay. Now we will be working with particles. So here's a particle with mass m, and it is located in the inertial frame here at some location R0. And in the non-inertial frame, it is located at some position R. We're also going to take the vector that connects the two frames here to be vector capital R. Okay, so like we said, S0 is inertial, but because this vector R here that connects capital R that connects the two frames, because it has a second time derivative that's not zero, that means that the S frame is non-inertial. So really what we get here is that this frame is accelerating with some acceleration A. Okay, so now let's take a look at what's happening here to this particle M here. We will have some forces that act on this particle. I'm getting quite a lot of arrows here, but hopefully you can make this out. There's a force F acting on this particle. So in S0, which is inertial, Newton's second law is valid in its normal form. So we can just write then that M R0 double dot equals the force F. Now we need to change into the non-inertial frame, and we do that just by simply noticing that R0 equals capital R plus R, which means that we can take the time derivative here, and then we get that first we take the first time derivative, then R0 is the velocity of the frame plus R dot, and R0 double dot is this acceleration A here plus R double dot. And we'll just make the substitution, and then we will get And we'll move this term over on the other side. And we'll obtain this is now Newton's second law in the non-inertial frame. So it looks similar to the form we're used to, but we have this extra term here. This extra term here is known as the inertial force. And that's the mass times the acceleration of the frame A. Now the inertial force is what we term a fictitious force. Which means that it differs from a normal force. It has some properties of a force, and so we put it over on the right-hand side of this equation, but it is not quite a normal force. So just to illustrate the difference between a fictitious force and a real force. First of all, the fictitious force is like a normal force, like a real force, in the sense that an observer that's in the non-inertial frame will experience this force as a real force. So a good example of that is if you sit in a car, for instance, and the car is going through a curve. As the car is turning, let's say to the left, let's just illustrate this here. Here's a car, seen from above, going through a curve. A passenger in this car will feel as if there's a force pushing on them towards the right, as if they're being pushed out against the outer door here on the right. And that's the fictitious force, ma. Okay, so for an observer inside the car, the passenger inside the car, this is indistinguishable from a real force. On the other hand, it is not like a real force because it doesn't correspond to an actual physical interaction. In other words, we can't apply Newton's third law to fictitious forces. There's no equal and opposite force to the inertial force here. So that's kind of how you want to interpret these forces. Mathematically, though, and it's supposed to be a double dot here, obviously. Mathematically, though, it's not too hard, not too difficult to deal with it. You just have to solve this equation instead of this one. And all that amounts to is adding in these inertial forces to the regular forces and then proceeding as normal. So let's do an example of this, one that we've seen before. And that's the pendulum in an accelerating car. And that's illustrated here. So we've already looked at this, so you should be familiar with this. We have a train car here, which is accelerating to the right with some acceleration a. Inside we have a pendulum subject to gravity, which is acting downward, and will then oscillate back and forth around some equilibrium. Now, if we look first at the case where the acceleration is 0, the acceleration is 0, then Newton's second law has the normal form, right? Just that m or double dot, that's the position of this pendulum bob here, equals the tension in the pendulum plus mg. where G is acting downward. We know how to solve this. We've done it using Lagrangians, and you should know how to do it starting from this point as well. What we get are oscillations around the vertical with frequency omega, which is the square root of G over L, where L is the length of the pendulum. And that is something that's well known, or at least this is true when the oscillations are small. So for large oscillations, the pendulum can actually be solved using normal analytical functions. Okay, so then the next thing we're going to do now is add the acceleration. So the acceleration is different from 0 with acceleration then. So in this case, Newton's second law takes on the form that we just derived with the inertial force in it. So we get mr double dot equals t minus, plus mg minus ma. That's our new equation of motion, and that's how it differs in the non-inertial case compared to the inertial case. Now what we can do here is we can see that, okay, both this term and that term, both the gravitational force and the inertial force are proportional to the mass. So we can just rewrite this in this fashion. Mr double dot equals T plus mg effective, where g effective has this form in the xy plane. These are its components, minus a and minus g. So the direction of g effective, if we were to draw it here somewhere, is something like that, like pointing towards the downward left. Now we know that we have equilibrium when the tension is equal to the other forces, right? Minus mg effective, or when they add up to 0. So that means that the equilibrium direction is the direction of g effective. The reason why in the inertial case the pendulum swings around the vertical direction is because the force of gravity points downward. Now we have replaced the acceleration due to gravity with an effective acceleration due to gravity, which points downwards to the left. So we're getting a phi naught here, and we can say that this phi naught is arctangent of a over g. That's a result that we found before, but now we can just find that by just looking at the physics of what's going on here. So that's part of the solution. The other thing that we can see is that, well, if this is the equation of motion, it looks just like this one. We can just by analogy see that if omega is the square root of g over L, then omega in this case must be equal to the square root of g effective over L. Now g effective, that's the magnitude of this vector. So that becomes the square root of a squared plus g squared divided by L. And that again is the same result that we got when we solved this problem with the Lagrangian method. We have that the pendulum is swinging around some direction which isn't vertical, but it's given by the arctangent of a over g. And the frequency is not the square root of g over L, it's the square root of this quantity here. This is the exact same result that we found before, although now we just found it much quicker just because we were able to draw an analogy between this non-inertial case and the known solution in the purely inertial case. So here you can see that at least in some cases, moving into a non-inertial reference frame isn't so bad. And we can, if we're lucky, map the non-inertial problem onto an inertial problem, but we already know the solution. In that case, we have to do very little work in order to come up with the right answer. In the next video, we're going to apply the same procedure, but to a slightly more complicated problem, that of the tides on the Earth due to the presence of the moon and the sun.